Dear colleagues, good afternoon. In my presentation, I will show the result of the study that is a part of the project funded by targeted program financing. The name of the project is shown on this slide. The main problem of the study is the need to move from simple observation to water resources to smart data analysis and decision support. For Kazakhstan, especially for southern and semi-arid regions, this problem is very important. Agriculture in these regions depends strongly on irrigation, stable river flow, and timely distributed water resources. This slide shows the main idea of the study. The aim of the study is to develop an approach for analyzing long-range dependence and forecastability of water resources time series. The study is based on data from automated hydrological monitoring. The object of the study is the data collected by bottom-mounted ultrasonic Doppler sensors. These sensors were installed on the Talas River. And these locations was chosen for a reason. The region belongs to arid and semi-arid areas. In such areas, water resources are very important for agriculture, for irrigation. And figure 1 shows the location of the sensors on the map. As you can see, regular and transparent monitoring of water resources is important not only for this local area but also for transboundary water management. And figure 2 shows the location of the flow meters on the Talas River in this study. 4 fixed ultrasonic Doppler flow meters were used, and they continuously measured by they continuously measured the main hydraulic parameters. So this is water depth, flow velocity, and water discharge, and also temperature. An important advantage of the system is that the measurements are automatic and regular. They do not need constant work by an operator, and this reduced the dependence on manual hydrological measurements. It also helps to create a digital archive of data. Then we can use it for analysis, trend detection, forecasting, and support for measurement decisions. However, automatic data collection does not mean that the data are immediately ready for scientific analysis. Sensor data may include irregular time intervals, missing values, noise, technical zero values, or incorrect measurements. So for these reasons, to the study pays special attention not only to data collection but also to data preprocessing. And the methodology of the study includes 4 main stages. The first stage is data cleaning, quality control, and conversion of data to regular time step. The second stage is a fractal analysis and the assessment of long-range dependence. The third stage is to analysis of seasonality, local dynamics, and multi-scale structure of the time series. And the fourth stage is comparative forecasting using different types of models. Thus, the study showed that automated monitoring data can be used not only to record the current state of water, they can also help to find hidden patterns, access forecastability, and develop future decision support models. And this slide presents the data used in the study and the results of the preprocessing. The original dataset included 27,296 records. They were collected from April 4, 2025 to March 20, 2026. And the measurements were most taken at intervals of about 10 minutes. However, the time intervals were not fully regular. In some cases, there were small differences in a few seconds. In other cases, there were larger gap between measurements, and sensors recorded several groups of indicators. These included water depth, water discharge from 4 channels, and water temperature for several channels, and flow velocity measured at a different point of the riverbed. This multi-channel structure is an important advantage of the dataset. It helps to take into account differences in water flow in different parts of the riverbed. For example, the water velocity in the central part of the riverbed can be higher than near the banks or in zones with hydraulic resistance. And therefore, the use of several sensors gives a more complete picture of the water flow. However, the original data could not be used in directly for time series analysis. First, the timestamp were checked. The record was sorted, irregular intervals were identified, technical zero values were analyzed. After that, the data were prepared for a regular time step. Then the data were reassembled in the 1 hour intervals. Smoothing and time interpolation were also applied. As a result, the preprocessed dataset was created. It contains 8,424 regular hourly observations without missing values. This dataset was used for further analysis and forecasting. Figure 3 shows the time series of water depth measured by 4 Doppler channels, as well as the average water discharge. It can be seen that the water depth changes unevenly over time. There are periods of increase, decrease, local jumps, and unstable parts. This shows that the series has a complex structure and needs preliminary analysis before forecasting. The third channel was selected for the main analysis. This choice was made for several reasons. First, it is a physically meaningful indicator of water depth at this specific measurement point. Second, it has a relatively stable behavior and less noise compared with some other channels. And third, the use of the separate channel helps to keep the physical meaning of the measurement. Figure 4 shows the hourly time series for the third channel after preprocessing. This series became the basis for fractal analysis, autocorrelation analysis, and trend decomposition, wavelet analysis, and comparative forecasting. Slide 4. And the next slide. In this slide, we present the key result of the study. It shows the wavelet scalerogram or the third channel time series and some forecasting results for the period from January to March 2026. First, let's us look at the structural analysis of the series to understand whether the hydrological time series can be forecasted. It is not enough to immediately use the machine learning model or a statistical model. First, it is necessary to understand the interval structure of the data. We need to know whether where there's a autocorrelation, seasonality, long-term memory, stationarity, and multi-scale fluctuations. Several methods we used in this study. The trended fluctuation analysis was used to estimate long-range dependence and the level of persistence in the time series. For the third channel series, the value alpha is equal to 1.22, and this indicates strong persistence and long-range dependence. In other words, the dynamics of the water depth are not random. At the same time, these results should be interpreted carefully. Values above 1 may indicate not only long-range dependence, but also non-stationarity or trend components. So therefore, additional methods were used. They include the automated Dickey-Fuller test and Kwiatkowski, Phillips, Schmidt, Sheen tests, and also seasonal and trend decomposition, autocorrelation analysis, and wavelet analysis. The wavelet scaleogram shows on this slide demonstrated that the depth 3 time series has a multi-scale structure. This means that changes in the water depth appear at different time scales, and there are short-term fluctuation, local changes, and also longer components. At the same time, no stable seasonality was found. This means that classical seasonal models may not have a strong basis for forecasting this series. This conclusion is important for choosing forecasting models. So if the series does not have a stable seasonal structure, models that strongly depends on seasonality may give weak results. For this reason, different types of models were tested in the study: statistical models, multivariate models, machine learning models, and neural networks. The data from April to December 2025 were used at the training set, and the data from January to March 2025 were used as an independent test set. The best results was shown by the VAR model. This model used not only the third channel series depth 3, but also related some other hydrological variables. For example, it means that temperature and maybe other time series. Also, the strong results was also shown by the ARIMA model with seasonal and trend decomposition. This is important because it confirmed the usefulness of preliminary time series decomposition. Among the neural network models, the best results was shown by the Gator direct current unit model. It performed better than LSTM according to both metrics. This means that for this time series, a simpler recurrent neural network architecture was better suited to the available data volume and the type of temporal dependence. Among the machine learning models, XGBoost performed best. It showed higher accuracy than random forest. Thus, the main result of the study, as you can see in this slide, is that the water depth of time series collected by automated Doppler monitoring can be forecasted. However, the quality of forecasting strongly depends on how well the model matches the internal structure of the data. In practical terms, that means that automated water resources monitoring systems should include not only data collected and storage models. They should also include analytical models such as the data quality control, fractal diagnostics, multi-scale structure analysis, and adaptive selection of forecasting models. In conclusion, this study showed the possibility of moving from sensor monitoring to an intelligent system of water resources analysis. The collected open dataset can be used for testing data, cleaning methods, time series analysis, assessment of long-range dependence, and comparison of forecasting models. Thank you for your attention.